I'm happy to be with you today to talk about the innovative design of steel moment frames. To introduce the topic, I want you to go back in time with me to the year 2000. Take a moment and picture what you were doing. Maybe you were in elementary school or high school, although for the youngest of you out there, maybe you hadn't been to any school yet. For others, maybe you were at your first job in 2000, or maybe you had just become a principal or partner at your firm. Picture what you were doing. For me, 2000 was a great year. I had hair back then. I got married in the spring, and in the fall, I started graduate school at UC San Diego. And I had wanted to attend graduate school in California because I was interested in seismic design, and especially in the steel moment connection testing that had been going on at UC San Diego in the late 90s. But 2 months before I started my graduate program at UCSD, FEMA 350 was published. And it appeared that maybe I had missed the boat. FEMA 350 was a culmination of the intensive work done on moment connections after the Northridge earthquake in the late 90s. And this document, it outlined all the do's and don'ts of special moment frame design. This became the basis for the AISC seismic design provisions for special moment frames. And those provisions really haven't changed that much since then. So I was worried, oh man, maybe I missed the boat. All the work's been done. But fortunately for me, there was some cleanup work to do in the early 2000s, even after FEMA 350 was published. For example, in FEMA 350, the RBS moment connection was pre-qualified, but only for columns up to 14 inches deep. Good luck designing in California with those kind of options. So one of the things that I did as a graduate student is I helped with doing connection tests for 4 different projects that wanted to use deep columns but were beyond what had been tested at the time. This photo shows a few of those deep column specimens showing up at the lab. These were for a hospital project in California. And you can see the RBS cuts right here on the beams. And then you also notice these were a little unusual. They had built-up columns from heavy plates. Most of the other deep specimens that we tested for other projects were just using wide flange shapes that were deep. Well, we ran the tests following the procedures in ATC 24, which are now found in Chapter K of the seismic provisions. For those of you who are not familiar with moment frame testing, this is an overview of the setup. The column was attached to the floor and the strong wall in the lab, and an actuator was attached to the end of the beam. The figure on the right shows the loading protocol that was used for the actuator that moved the end of the beam up and down to impose rotation on the beam to column connection. In order for the connections to qualify, they need to go through 4 radians of rotation without significant strength loss. So that was probably out here somewhere on the loading protocol. So on the days of the tests, there's always a lot of excitement at the lab. Lots of people came to observe. The engineers that designed the hospital were there. The engineers that were doing the plan review for OSHPOT were there. While we would run a test, we would monitor real time the load that we were putting in the actuators, as well as the deflection to produce these hysteretic plots. And this is pretty typical of what the plots would look like. Usually it would be elastic for small drifts up to about 1%. Around 2 or 3%, we start to cap out on strength. And then after that, the strength comes down a little bit. And the decrease in strength, that's caused by the local buckling that's occurring in the plastic hinge of the beam once we get out to large deformations. On this particular test, there was the typical local buckling, but the strength didn't drop too much. We got to 2 cycles at 4% drift, and there was much rejoicing because the connection had passed and they were going to build their hospital as planned. And so these were the first kinds of experiences that I had with steel moment frame connections. I tested many of these connections before I even was that familiar with the design provisions, and I hadn't ever designed any still moment frames prior to doing these tests as a graduate student. Now, at the same time I was doing these project-specific tests, there were other researchers that were investigating deep columns and RBS connections. And so by the time that the first edition of AISC 358 was published in 2005, RBS connections were pre-qualified for up to 36-inch deep columns, and that was my small contribution to the world at that point. This document we'll be talking about a lot throughout the presentation, AISC 358, pre-qualified connections for special and intermediate moment frames. The first one came out in 2005, and there have been regular updates since that point.